Hello, we are from Van Horn Aviation, and we will be presenting today on the installation and inspection of composite rotor blades. We'll have two presenters today. I am Dan Belber. I'm the flight test engineer at Van Horn, working on development and certification of rotor blades. I also support customer installs with track and balance. And in a previous position, I designed the blades and did structural testing. I've been with Van Horn for 7 years. And before that, I was with Sikorsky Aircraft for 7 years, degrees in mechanical and aerospace engineering. I've completed the training programs for the three big track and balance equipment manufacturers. I have my private pilot cert, and I'm a structures DER.
And my name is Terry Tyner. I'm the flight operations manager, the flight test pilot. We do also customer install support. Any questions that you have on issues, just like Dan, we're the two that you would reach out to. I'm also the chief inspector for the Van Horn repair side of the house, and it's an FAA certified repair station. I've been here a little over a year. I have 36 years of rotorcraft experience, commercial pilot, CFI, and all that. Hold an FAA airframe and power plant license with inspection authorization. And I have going on 25 plus years of track and balance experience.
So briefly cover what we're going to talk about today. We'll introduce Van Horn Aviation for anybody who doesn't know us. We'll talk about installing rotor blades. We'll give you some tips on track and balance. We'll introduce you to tracking wedges, which replace trim tabs. We'll talk about inspecting composite rotor blades and what repairs are available for composite rotor blades. So we are Van Horn Aviation. We've been around for over 20 years, about 40 employees strong, located in Tempe, Arizona. We have a flight test hangar at Falcon Field in Mesa, Arizona, and our repair station is co-located at the Tempe facility. Our mission is to enhance legacy aircraft through improved composite rotor blade design. So what that means is we look at aircraft that have been around for 40, 50 years sometimes, and we develop rotor blades with the newest efficient airfoils, carbon fiber construction, abrasion strips, which cover the entire leading edge of the blades. And we generally produce products that have a longer service life than the blades that we are replacing. Currently in production, we have main and tail rotor blades for the Bell 206 Jet Ranger and the Long Ranger, and we make a tail rotor blade for the UH-1 Huey. We're currently flight testing a tail rotor system for the AS350, and we are in development of a main rotor blade for the MD500F model. So I'm gonna talk a little bit about our blade design philosophy. Generally, we want to provide some improvements, but we want to match the behavior of the blades that will be replaced. So some of our improvements, I talked about an improved airfoil. So we're extending the pitch range where you get laminar flow. This gives you a better performing airfoil. So you'll generally get more lift from that blade. Tapered and swept tips. So in that picture, you can see the tip geometry sweeps aft and forward at the tip, and that gives you better acoustics, so you'll have a smaller noise signature. And carbon fiber, in general, when it replaces aluminum, you get a better strength to weight ratio. So for a given weight, you will have a stronger product, and that's usually why we get longer retirement lives. Better fatigue performance. You reduce corrosion issues with carbon fiber, and generally better process control. You will have a more consistent weighted blade than, let's say an extruded aluminum counterpart. But we are trying to match the behavior of the blades we're replacing with different materials. So we try to match the stiffness and the inertia. That way the blades generally react the same in the air, same diameter, same chord length. There will be minor differences because of the material change. And that's why we have to provide new track and balance charts. But in general, the feel of the aircraft should be pretty much the same. So now I'll talk about installation of the rotor blades. So the main blades that we produce are for a two-bladed teetering rotor system. So when you have a teetering rotor, you have flapping motion about a trunnion. And the first step in the installation is to zero the trunnion with shims. You really want to make sure that that trunnion is perfectly centered. That's critical for your install. And then you assemble the blades onto the hub and you put them on a fixture to align them in the sweep direction. Also very, very critical to ensuring a good install, and it will prevent vibrations further on in the process. You can also static balance the system, usually from a hanging apparatus, and adjusting the weights in order to get it to sit straight and level. Then you install the hub with the blades attached on the aircraft. You always want to check your rigging, make sure that everything is within limits. It's best practice to zero the pitch lengths, especially if you're going from different generations of blades or different types of blades. You really want to set the pitch lengths to the nominal length per the maintenance manual that you're working with. And anytime you install blades, you want to zero the trim tab so that you start from a known position. And then once you are ready to start the aircraft, you check track at 100% ground. So that means you're sitting on the ground at 100% rotor RPM. And if the tips of the blades don't run at the same tip path, if one's flying higher than the other, you adjust the pitch lengths to level them out. And then you address lateral balance. You have accelerometers installed that are measuring balance in the lateral direction. And there are weight adjustments to bring those vibrations down. And then in the vertical direction, you are also measuring vibrations. And typically this is in forward flight. You check it in hover, but you're making your adjustments based on vibrations in forward flight. And again, there's adjustments to modify the vibration there. And then once everything is at a low vibration, usually below 0.2 IPS, which is inches per second, you will check your RPM during auto rotation at a given speed per your maintenance manual, and you make an adjustment for your RPM. There's charts provided, and you adjust that speed by moving both pitch lengths up or down to make that adjustment. And then you check the settings of your flap restraint as well. Tail rotor blade installation for the aircraft that we are providing blades for, it's a hub with removable blades. So you install the blades on a hub, you static balance that assembly, again, usually with a hanging system or something sitting on a balancing ball with levels, and you adjust the weights off of the aircraft. And then when you go to install it on the aircraft, it should be pretty close to, the vibration limit with small adjustments. So you'll run it up to 100% RPM on the ground, and you'll make fine adjustments to bring your vibrations down.
Dan, I'd like to point out one thing on the tail rotor balance for everybody. The two or the balance techniques he told you, the two units out there are the Marvell balancer and the Bell bubble balancer. We highly recommend the Marvell, but we've had a few people just put the blades on and try to balance them, and you really have to static balance the set, and you'll have a lot better luck with your dynamic balance procedure with whatever machine you use.
All right, so this talks a little bit about the adjustments that you make to modify your vibration levels. So this is specific to the 206, but most aircraft have similar adjustments, you know, whether they look a little bit different or are located differently. You know, it all does very similar things. So for the lateral vibration, it's all weight adjustment. You're either adding weight inside the attachment pin. Sometimes there's a bracket that you can add weight to, but it's along the center axis of the blade. The chord balance adjustment is weights added to the side of the system. On the 206, it's attached to the side of the yoke. You can also adjust the sweep of the blades. This does affect some other things. So, you know, you can choose between chord balance weight and sweep to make any chord balance adjustments for your lateral vibration. For vertical vibrations, the main adjustments are the length of the pitch links. Then there's either trim tabs or wedges. We'll talk about wedges later. Trim tabs are the typical you know, industry standard. It's a metal sheet that sticks out past the trailing edge of the blade, and you bend it to a certain angle to make the adjustment needed. And sweep actually does affect your vertical vibration. So that is an option once you start to get into your balance runs. Tail rotor balance is much simpler. It's all weight driven. So you add weights either in a span or chord location, and you can reduce the vibration mostly. We've put out a technical bulletin, which it specifically applies to our blades installed on a 206 aircraft, whether it's a Jet Ranger or a Long Ranger. But there is a lot of good information on here for track and balance in general. So you can follow the link here to find this bulletin and use it if you are having trouble with troubleshooting or anything like that. The balance equipment available when you're doing track and balance, there's accelerometers that are installed at different points in the aircraft. The maintenance manual will specify the location. These will give you a reading in inches per second, which is actually a velocity. So the balancer is doing the calculations to make that conversion. You will have a rotor tachometer reading the RPM, but it's really indicating where the blade is located in relation to the vibration signature. So it tells you where you need to make your adjustment, whether it's chord or span, and that's critical to putting weight in the right place. As for tracking, this is done when you do your 100% ground track, or you can also check track when you're in flight. If you just want to have a better understanding of how your blades are flying. This is done with a strobe system with reflective tape at the tips of the blades, or an optical system, which does it automatically and reads it to your balancer. Diagnostic Solutions is a company that we've worked extensively with. They've actually come out and created algorithms for our blade, and there's built-in programs for the Vibrex and the VXP. There are other balance equipment manufacturers. The Army has produced RADs. There's Microvibe and ACES. For our blades, you can use the OEM programs for any of these systems. Any smart balancer will have the ability to adjust their algorithms based on the data that you produce from your first run or two. So all of the systems do apply for us. Terry, you want to take this over?
Yeah, sure. So on your main rotor balancing, our advice on the two-bladed systems is to wait for a calm wind day, clean blades. Don't rush it. Don't skip any installation steps. Get to 1P versus 2P vibration. The 1P is what you're measuring with the various equipment, whether it's the Chadwick or 2000 VXP or Microvibe. And that's what you're adjusting when you are adjusting your pitch links or your tabs for your forward flight maneuvers, like Dan mentioned. As you get those blades in a tighter path or more closer together in track, you will see the 2-per come up. So this is why we say it's not necessary to try to get it below 0.10. Sometimes we find the overall ride is better at about 0.12 versus getting more of a jarry ride. So, choose carefully on how far or how low you want to get the 1P vibration down so you don't increase the 2P. Don't chase a perfect track for the above reason. And if you're having difficulty reducing the vibration with adjustments, again, slow down, make one adjustment per run, check the install of the balance equipment, double check your torques, check that hub trunnion alignment, that's very critical. Check looseness, play and bearings around your source plate and any loose fasteners, any looseness in that system, any looseness in the landing gear, that's going to cause increased vibrations. And a small hop at a hover, or if you're getting a vibration on the polar chart that's in the shaded area and just not reacting right, we recommend you check the TT strap shimming, loose TT straps, because the shimmings aren't tight will cause that vertical hop and a hover. Sometimes you can turn that into a hover the bird in a tailwind, and if you see that hover vertical ips go up, that's a telltale sign that your TT strap shimming is loose. On hub alignment, this is really critical on the two-bladed system. We use the string method that's pretty much in the Bell manual. You install the hub on the alignment stand with the pitch horns fixed. You adjust those grips based on those pitch horn settings to where the grips are level with the yoke. And sometimes you can use a protractor there to measure that level and get them exact. Torque those blade pins per the maintenance manual. Install the string alignment kit posts in the blade pins. Attach the string outboard of the alignment rivets such that the string crosses over the center of both rivets on each blade, and it's tight enough that it contacts nothing but the posts. You'll want to adjust the latch bolts to align the blade such that the string is barely touching the posts or a gap less than 0.005 of an inch. And that's after everything is finally torqued up. This is a slide is an installation example based on our VHA test ship. And what you're seeing here is two charts, a 60-mile-an-hour vertical and a 100-mile-an-hour vertical. So the pitch links are generally used for 60 and the 100 is for tab, but we're showing the interrelationship on what the move lines show between doing either a tab or a pitch link at the given airspeeds. You'll notice on the left of the screen, you have position number 2, which would have been your starting IPS of about 0.95 at 215, 220, and a up tab would have moved it generally about 2 inches or 2 degrees of tab. This would be the one with the trim tabs on them, would have moved it in towards the center. You work that combination there, again, at 60, preferably with pitch links, and then you'll plot your 100-mile-an-hour chart over here and try to use tabs to bring it in. So these are just a sample of the polar charts, and we have these broken down in our technical bulletin for our best practices for track and balance. This is another customer installation example of 60 to 100. You can see here on the polar chart under 60 that he used pitch link, or I'm sorry, tab to go from his IPS position of about 1045 at 0.35, and he used a pitch link to bring it over to around 1230 at 0.21, and then he used a tab to bring it over to position 2, and then he used a pitch link to bring it down towards the center. So sometimes you can work the 2 pitch link and tabs with each other to walk it in the center. One of the biggest things, whether it's OEM blades or our blades, is the 2-per. You get that, you make all your adjustments with your pitch links and your tabs, and you just feel kind of a rough, jarry ride. A lot of times that 2-per increases. And that's why we said earlier, just don't try to go for 0.05 if 0.1 is a decent ride. If you get that 2-per up there and that jarry vibration, and you're just not sure that that's the best you can get it, you really want to go in there and check your source plate, all your frictions, your source plate uniball friction, your isolation mount bearing, your drag link bearings, your hub trunnion. You want to check for play in the bearings of the control rods, the uniball bearing, and your source plate tilt friction again. Check your torque, your tail boom attach bolts, your latch bolt torques, your elastomerics, especially on the Long Ranger. Check for loose components. Now, this is a big one. Anything loose on the bottom of that aircraft, landing gear, if you've got ag spray equipment, tanks, anything loose in there will exasperate that 2-per quite extensively. So check your flight steps, your cargo hook bungee, your battery, your ballast weight, high skids or pop-out floats, any kits, anything attached to the after forward cross tubes. One of the big things that we find is quite aggravating of the 2-per is the rear saddles. The rubber's worn or the clamps are no longer clamped up in there, and that will 100% cause a heavy 2-per. Improper assembly on the spike striker plate or the TT straps. Those are all other things that can cause an excessive 2-per. Okay, now we're getting to the tracking wedges. Before we had the trim tabs, we've since removed those, and we've adopted the tracking wedge system that the Army's been using. Basically, it replaces the metal trim tabs, and it's a 6-degree wedge bonded to the blade's trailing edge. You choose the length using the polar chart. You mark the location outboard or inboard, whatever location you need to make the adjustment on. Scuff and clean, and then pill and stick. 3.5 inches of wedge equals 1 degree. Max wedge at any location is 24 inches. Now, these wedges were developed for the AH-64 Apache composite main rotor blade. They have approximately 2 million flight hours in operation since '09, and they've been qualified for use on the AH-64, CH-47, UH-60, and the AH-6 platforms. And we've had very good luck with them. Their predictability is right on target if you follow our polar charts.
And one thing that's nice about the tracking wedges is the fine adjustability. With a trim tab, you try to bend it 1/4 of a degree. Sometimes it washes out, or sometimes it springs back, or something like that. With a wedge, you can cut it to the nearest 1/2 inch or even 1/4 inch, and you're talking about a small fraction of a degree that you're modifying. So it's a very finite adjustment.
And you can also install these on the upper or lower position of the blades. You're either making the blade climb or dive, just like you would with a trim tab. Station locations for those wedges. The blades that we're shipping out now will have station location marks on them. For the 206B, the outboard wedge position is 49.5 inches. The inboard position is 121 inches as measured from the tip. For the Long Ranger, it's 55 inches for the outboard wedge position and 143 for the inboard position. This here is an example. As you can see, it's the same type of polar chart that you're used to using on all your track and balance. At 60 miles per hour, the vertical chart, you use the pitch link. And by moving it, by adding a wedge up or on the bottom of the blade, make it climb or dive. And then at 100 mile an hour, you can either use pitch link or outboard wedge. And we kind of show the how much wedge in inches per whatever position it is on the chart based on how many IPS that you're showing. When you're in the shaded region of the chart, inspect for looseness in the hub, pitch links, balance equipment. Most blades should require only pitch link adjustments and little, if any, outboard wedge. If track cannot be achieved, we'll go to page 2. One of the things that I like to point out here is our best practices technical bulletin has all that's in it. It's really good, and it kind of gets into more advanced stuff. So if you need questions, don't hesitate to look at our tech bulletin. This chart here is for the 100 mile an hour vertical chart. The left one on your screen, and again, is for pitch link and outboard wedge. The one on the right is for inboard wedge and or sweep. If you notice when you use inboard wedges, it's always equal and opposite. So if you're going to go 6 inches of wedge up on the red blade or target blade, then you're going to go 6 inches down on the blank blade. We have sweep in here, but that's going to be more for advanced. We try to get you to steer away from that sweep unless you're kind of running out of any other options. Our blades, due to the process control that Dan mentioned earlier, and their properties, they're pretty reliable, and the track and balancing usually comes in pretty quick with the standard charge.
Right. So the chart 2 is mostly if you find yourself in the shaded region of chart 1. So it gives you an option of how to get out of that shaded region, because you really can't get out of that region with just a pitch link or an outboard wedge adjustment. So we're just providing other options, but typically if you're in the shaded region, these other moves like inboard wedge or sweep are really compensating for some looseness in the system that causes the vibrations in that direction.
Okay, the next topic's going to be Van Horn repair. We're a FAA repair station. We're pretty much solely on our main rotor and tail rotor blades. It was established in 2014 and is co-located at our VHA Tempe facility where we do all the manufacturing. And again, we pretty much do only our main and tail rotor blades. Impact tolerance of composite blades. The metal versus composite construction differences are carbon fiber layers laid up against a high density foam core. Others may have honeycomb. No D-spar like metal blades means composite blades respond differently when damaged by impact. Often the ruggedness of the composite blades will keep the blades together after a strike. We've had circ fittings go through tail rotor blades and tail rotor strike cactuses. We actually had one Huey blade recently. The very large Seuss fastener went right through the tip. A lot of times pilot don't even know they had the damage that has occurred. Rotor blade handling, the most visible impact damage caused by in-flight vegetation bird strikes are from aircraft handling, hangar rash. Because it is carbon fiber composite, you don't want to set anything on them. You don't want to clamp them up, thinking you're going to hold them on with wood clamps. Otherwise, you could cause crush damage of the core or edge damage. Nothing should be placed on or dropped on any composite blades. Continuing on, the damage may not be visible. Nickel abrasion strips do not deform easily. They may not readily show evidence of an impact. If impact damage is suspected, look for leading edge damage, shiny areas, paint residue marks, paint cracks following at the edge of the abrasion strip, radial type cracks in the paint finish. And those radial paint cracks, from what you're used to seeing on OEM metal blades, just look like a fine line paint crack. But that's one of the reasons that we will go in and tell you to do the tap test for any hidden damage. All the above indicators are that impact damage. And again, that's why we do the tap test. The next slide kind of shows you a picture of it. Normally you would just think that might be paint or erosion or something, but any area of void or delamination or internal damage is suspected around any unusual paint cracks where the blade may have had in-flight contact with an object. We'd want you to go in there and do a good tap test. On the tap inspections, you need to conduct it in a quiet area with a tap hammer or coin. The composite fibers and the core material is going to be a little different sound than what you're used to with metal blades. So you want it in a very quiet area. You want to use the ICA manual diagrams of the internal ply drop-offs, because there's different in sounds from different intervals or internal structures of the tail blade. So as you can see in the chart here, we're kind of pointing out the different thicknesses and plies, and the end of the tip closure is going to sound a little bit different. So with practice and comparing it to another blade, you'll come up with a good technique and a good ear to kind of differentiate what's a void and what is not. The UH1 doesn't have a diagram. You can reach out to us at any time and we can talk you through that if you got any suspect areas. Early 206 tail rotor blades often sound like there's a void over the tip weights. Again, that's due to that end of the tip closure at the top of the picture, and a little different sound there is normal. Okay, on this next video, we're going to show you a tap inspection demo. You can also find the instructional video available on the VHA website YouTube channel. We have a lot of other videos on there too.
Yeah, so I'm going to start here at the outboard end, and like I said, you'll hear a nice solid tone again as I work my way inboard, and then listen for the tone change right as I cross the crosshatched area here. You'll hear a more flattened, deadened tone, kind of a buzzing sound, but it should be pretty clear. So you hear right in that area, it goes from this solid sound to this buzzing sound. So that's all we're trying to do is determine right where that starts, and right there is about the length of your delamination.
Can an operator do this inspection with the blade installed on the helicopter, or what kind of conditions do they need to get the best results?
We strongly recommend taking them off the helicopter so that you can put it on a nice flat surface, and preferably be in a quiet area so you can really hear the tone changes without a lot of background noise.
Now, it was pretty clear to me hearing the sound of that tap right now, but what should an operator do if they're not sure if they are hearing a delamination or not?
Sure. So what some operators have done and works really well is just to take a video with your camera phone or whatever you have available of you doing the tap test, exactly like we showed it here, and send it into us and let us give a listen. Usually it's really easy to hear where it changed, and we can help show you where that's occurring and what to listen for. Tap along the length essentially of the weight pocket, preferably with a tap hammer, and start from the outboard end and work your way inboard. That way you're starting from a known good area, and then you'll hear the tone change as I go inboard over the delaminated area. So you might have noticed that right in this area, it went from a solid tone to a more flat, buzzing like sound.
Mm-hmm. Yeah, I can hear that.
And if I go back and forth, you can kind of gauge about where it starts. So somewhere kind of right about there is where the delamination starts coming from this end. So we would say that that delamination is about 2 inches long.
For composite materials in general, you want to prevent erosion down to the composite material. You don't want exposed carbon fiber. It's inherently susceptible to UV damage, and especially if you have exposed core or even the carbon fiber, you want to avoid exposure to water intrusion into the core. Could cause a lot of problems, could change your weights, and water moving around under CF can cause more damage internally to the blade. So protecting the surface of the blade is very important. You always want to maintain full paint coverage over the composite surface. So this means periodically check the paint surface, look for damage, and if there is any exposed carbon fiber, you want to do a touch-up in a timely fashion. You can even do this with a rattle can for a temporary fix, and if necessary, an epoxy primer before applying some polyurethane paint for a more durable solution. And you can reference any one of our ICA manuals for detailed instructions on spot finishing. This is a diagram showing our leading edge abrasion strips on main blades. In general, if your abrasion strips are non-structural, the key to operating or continuing operation with them is to prevent water intrusion. So we have allowance in our instructions for continued airworthiness to seal any cracks in our leading edge abrasion strips because they are non-structural. So any paint cracks around the edge or cracks in the middle of the strip, first thing you do if you see a crack, you do a tap test inspection. You make sure that there's not any voiding. If there is, then you do have to replace that abrasion strip. And that's something where you send it back to us to do that operation. However, if there is no voiding, we do have allowance to apply some BHAF to the crack, around it by about a ½ inch in every direction to seal that crack from water intrusion and protect the composite surface and the underlying core. We have made a lot of instructional videos. They are all available on our YouTube channel. The link is provided there. We've done videos on removing trim tabs. If you have blades that have trim tabs and you want to transition to the wedges, or if your trim tabs have an issue, cracks or debonding, that removal process is documented on YouTube, and you can follow that procedure and transition to wedges.
Dan, can you back up on one slide? Sure. Make sure we point something out. Can you explain, this covers the abrasion strip repair, and it covers the full length or just the tip for the cracks?
This does cover all the leading edge abrasion strips. if there's a crack on the main strip or just the tip strip, they are addressed the same way to prevent water intrusion.
And on our leading edge strips, the early blades were made out of stainless steel.
Yeah, so we've transitioned away from stainless steel to Inconel, which has better fatigue properties. So the new Inconel strips, we've not seen any of these cracks. This is a high load in the leading edge, and we've been able to prevent this with improving our nickel production and transitioning to stainless steel for the leading edge.
Yeah, so all new blades produced will have the Inconel.
Correct.
Leading edge strips.
Yep.
Is there a limit to how many cracks that we can?
There are no limits as long as there is no delamination underlying, but you will have to regularly inspect for delaminations if there is a crack present. All right, that covers our presentation. If you want any more information, we provide it on our website. In our instructions for continued airworthiness, we have more tech bulletins available and best practice documents. So feel free to reach out, and see you later.